Good afternoon. This is our lecture in game theory. This is an asynchronous lecture meant for the time slot of Wednesday. And we move beyond strategy, which we have talked about, and we start talking about hold on, about how to solve games. We'll start off with the basic concept, which is the concept with the minimal set of assumptions, and that's what's called rationalizability. I think I'm following the examples in Gibbons on this part. Gibbons doesn't use the term rationalizability. Watson does, so you can read both Watson and Gibbons section 1.1.b, okay? So Gibbons 1.1.b and then Watson on rationalizability. Okay. And what is driving us is, what do we think a rational player would do in a game? But sometimes it's actually easier to say, not to say what a rational player would do, but what a rational player will not do. So can we rule out certain behaviors? Can we rule out certain behaviors using some simple assumptions? Around rationality, okay? So we thought, right, that in a simultaneous game, so think about the most common game used, which is prisoner's dilemma. Everybody has heard of this game, right? There are two players. Do you remember this game? That there are two players. These are two possible criminals who have been caught in the act of committing a crime. The police chief does not have enough evidence to convict them. What he does need is a confession. If he doesn't get a confession, he can convict them on some minor crime, okay? And he needs confession of at least one person. He doesn't need the confession of both people, and it's not. So the prisoner's dilemma is from the point of view of the two prisoners. So the prisoners, using Gibbons things, they can stay mum, which is they do not talk, or they can think, which is they can rat on the other person. It's a simultaneous game, so this is player one. This is the same information set, remember, right? It's a simultaneous game. And then the second player also can go mum and think. So if I write the normal form with the following the usual convention, each player has just one decision to make. It's mum and think. Mum and think. Okay? So each player has only one decision to make. It's simultaneous. So that's what a normal form would look like. And I will kind of go through the payoffs. Okay? So what is a typical set of payoffs in a prisoner's dilemma? We can keep, I can put it in many ways. So I'm going to do it in the context of prison terms. So remembering the convention that the first payoff represents the payoff of player one. This is player one. I'm not going to write it because that's going to be our standard convention of player one and player two. If both players go mum, player one gets 1 year in jail, player two gets 1 year in jail. They're convicted on a minor crime. But remember, they are people now in separate rooms and they're playing a simultaneous game. So there's no communication. There's no coordination. So that's really the essence of the simultaneous game. You can't observe what the other person is doing. You can't talk to them. You can't do it, right? So if they go mum, both go mum, you get -1, -1. If, however, the other person goes monk, so if player two goes think, so the player two rats on you and commits the crime. This is what the the DA, the prosecuting authority, tells these prisoners, hey, listen, if you tell me the truth as to what you are doing, I will let you go free. Okay? However, if you don't tell me and the other person tells me, then you are really going to get the hammer, right? So let's write those payoffs. So if player 2 goes funk and player 1 goes mum, player 2 goes free, that is a payoff of 0, no prison term, and you get hammered, player 1, because you did not confess, you stayed mum while the other player ratted. It's a symmetric game. If both players think, if both players simultaneously convince this is the regular prison term, -6, -6. Okay, so that's kind of, you don't get a penalty for not being cooperative, right? If the other player thinks and you stay mum, then you pay this extra penalty of -3, so you get -9. If you go think and the other player goes mum, what is it? It's symmetric, so then you get off scot-free, player 1, if player 1 thinks, and player 2 gets -9. That's the classic prisoner's dilemma. I can change the numbers and I can give you, as long as that general pattern holds. So now let's look at what is the player supposed to do. And what I want to iterate here is the concept of what is called a strictly dominant strategy, or equivalently a strategy that is strictly dominant strategy, or a strategy that is strictly, which is the converse of it, dominated by another strategy. Okay? And here I want to introduce the term beliefs. Now the term beliefs is used quite commonly in our everyday language. I believe such and such. I believe such and such. Well, in game theory, a belief is a probability distribution. So my belief is, what is my belief that player, let's say I'm player 1, that player 2 will follow a particular action. So I'm player 1, mum, think. You are player 2, mum, think. So there are only 2 actions. This is the entire action space. Remember, this represents the entire game, this normal form. There's no other event that's going to happen besides player 2 playing mum or think. So a belief is a probability distribution. Now it's only a 2-point distribution, so it's pretty simple. I can put a probability P that player 1 will play, player 2 will play mum, or player 2 will play think. So it has to be P plus 1 minus P. The probabilities have to sum to 1. The idea of a strictly dominated strategy is that there exist no beliefs that will make me playing this strategy as a best response. Okay? So let's look at that in the context of the prisoner's dilemma. In the context of the prisoner's dilemma, what I would claim is that for player 1, and this is a symmetric game, so this will also hold for player 2. For player 1, there is no belief on player 2's actions that will make player 1 play mum. Okay, so let's take a look at that. Let's say that player 2 plays mum. So if player 2 plays mum, so then we are in this world. What are player 1's choices? If player 2 plays mum, player 2 has to decide between mum and Fink for herself. What is she going to do? Well, we know, right? Fink dominates mum. And I would say strictly dominates, right? It's 0 is greater than -1. So, which means player 1 will never play mum if she thinks player 2 is playing mum. Now there's only one other possibility, which is player 2 plays Fink. Okay, so we are in this world now. These are the player 1's payoff if player 2 plays Fink. Well, in this case, it's also very clear. If player 2 plays Fink, then player 1's what I would call best response in choosing between mum and Fink is to play Fink. Strictly, right? -6 is strictly greater than -9. It's not greater than or equal to. It's greater than -9. So the point is, there are only two states of the world. Either player 2 plays mum or player 2 plays Fink, or with certain probabilities, player 2 can play mum or player 2 can play Fink. There is no set of beliefs that can lead to player 1 not playing Fink. So what we say is mum is strictly dominated by Fink for player 1. Right? It is not rational for player 1 to play mum. That's our definition of rationality. Our definition of rationality is our first definition. We can talk about it a lot. You know, von Neumann had defined rationality in economic theory. We have axioms of rationality, and we'll talk about them as we move along. But here, the definition of rationality is rational players do not play strictly dominated strategies. Equivalently, we can say that mum is strictly dominated by Fink, and Fink strictly dominates mum. Okay? Now look at it from player 2's point of view. Let's write this thing again. Mum, Fink. I'm not going to write player 1 and 2. You know which one I'm talking about, right? Mum, Fink. Just to make sure I write the same payoffs. -1, -1, -9, 0, -6, -6, 0, -9. Now, here's the interesting part. And what we are doing is we are assuming not just rationality, but not just rationality, but common knowledge of rationality. And what do I mean by that? What I mean is one is rational. If one is rational, we know he won't play mum, right? Common knowledge of rationality says the following. Not just one is rational, but two knows that one is rational. Okay, so this is really important, okay? So this is now a higher order of an assumption. Not just one is rational, but two knows that one is rational. If two knows that one is rational, she is not going to play mom, which means from two's calculus, she can take out the strategy. She knows one is never going to play it. So as far as two is concerned, the game is what is just left, right? Now we know one is rational. Sorry, now we know that two is rational. So what is two going to do? Two is going to compare, two has just a very simple decision now, just to compare this with this. -6. So two has to now only compare -6 with -9. Well, we know -6 is strictly greater than -9, which means a rational 2 will also not play mum. So coming here, a rational 2 will not play mum because -6 is greater than -9. Boom, boom. So rational 2 will not play mum. So the only strategy that survives, and this is the process that we have just followed, what is called iterated deletion of strictly dominated strategies. Right? Iterated deletion of strictly dominated strategies is think. So rationalizable strategies, so Watson makes a big deal about it, Gibbons doesn't talk about it. I will make a little deal about it, about the concept of rationalizability. Rationalizable strategies are ones that survive iterated deletion of strictly dominated strategies. Okay? So in our case, this iterated deletion leads in PD, the prisoner's dilemma, this process leads to a unique outcome. Now that's not always the case. So pretty nice, right? This is very fascinating, right? Rational players go think, even though if they had both stayed mom, they would have gotten -1. From a joint outcome point of view and from an individual benefit point of view, mom is strictly better than think from a joint point of view. However, from an individual rationality point of view, your best interest leads you to an outcome which is suboptimal. That's the beauty of the prisoner's dilemma as an example. And we'll keep on continuing back to examples like this, and I'll talk more about the prisoner's dilemma as well. Okay? Hold on. Okay, I want to move on and work through some more examples. Let me just pull them up. Give me a second. Okay. Here's another game, simultaneous game. I'll just write out the normal form. So this is a more generic game, up, down, and player 2 can go left, middle, and right. Okay? And I'm going to write the payoffs. So if player 1 plays up, player 2 plays left, it's 1. Player 1 gets 1, player 2 gets 0. We should be familiar with this convention. Up and middle, player 1 gets 1, player 2 gets 2. Up and right, it's 0 and 1. Down and left, 0 and 3. Down and middle, 0 and 1. And down and right, 2 and 0. So this is the game, simultaneous game, simple strategy space. We have written it out for each person. Okay, now let's apply these principles of strictly dominated strategies to this example. Think player 2's problem. Okay, can you spot a strategy for player 2 that is strictly dominated? Well, let's go through it one by one. It's a simple enough problem that we can go through the whole problem. Let's compare left to middle. Compare left to middle. Okay? Player 1 plays up. Player 2 plays left, gets 0. Player 2 plays left, gets 0. Player 2 plays middle, gets 2. Yeah? Okay. This is 1, by the way, not 7. Okay, so if my belief is that player 1 is going to play up, then middle is better. However, if my belief is player 1 is going to play down, then what do I do? If player 2 is going to play, if player 1 is going to play down, I am here, right? Then left is strictly better than middle, right? 3 is greater than 1. So it's not clear. There is a set of beliefs under which left is better than middle, which is if I believe player 1 is going to play, if middle is better than left, is if I believe player 1 is going to play up. There is a belief, if I believe that player 1 is going to play down, then left is better than middle, right? So left and vice versa, middle does not strictly dominate middle and vice versa. So on the basis of rationalizability, I cannot eliminate either one. Okay? So not good. But let's try middle versus right. If player 1 plays up, so again looking at it from player 2's point of view, if player 1 plays up, middle is better than right, strictly, right? Is better than right. 2 is greater than -1. Sorry, 2 is greater than 1. If player 1 plays down, then what's the case? Hey, middle is better. Middle is better again. One is strictly greater than 0. So a rational 2 will never, and I mean never, play right. Never play right. I mean, there is no set of beliefs that two can have about one's actions that make playing right a best response. Okay? Let me just rewrite this whole thing again. So just rewriting it, 1 0, 1 2, 0 1, 0 3, 0 0 1, 2 0, right? So this is up, down, left, middle, right. So a rational 2 will never play right because right is strictly dominated by middle. So I can, rule this out. This is never going to be played. Now invoking common knowledge of rationality, player 1 knows that 2 is rational and therefore will never play right. So 1 now faces the modified game as above. Okay? So what's 1 going to do? Well, if 2 plays left, up is strictly preferred to down in this modified game, right? 1 is greater than 0. If 2 plays middle, up is still strictly preferred to down, right? To down, 1 is greater than 0. So a rational 1 who knows that 2 is rational will never play down. So the new game now looks like this. 1 0, 1 2, 0 1, 2 0, 0 1, 0 3, left, middle, right, up, down, we know a rational 2 is not going to play this, and knowing that a rational 1 is never going to do this. Now, 2 is rational, and, okay, so this is invoking a second degree of common knowledge. 2 is rational, knows that 1 is rational, and knows that 1 knows that 2 is rational. Okay, this is common knowledge. So common knowledge is important. 1 knows that 2 is rational. So now this is the game left for 2. What you see up there. And now it's very clear. A rational 2 will play middle. 2 is greater than 0. Boom, boom, boom. Again, this is an example, the rationalizable set. The rationalizable set is unique. It is up, player 1 plays up, player 2 plays middle. That's what it is. So that's the only thing that survives iterated deletion of strictly dominated strategy. But, okay, so let's just take a second to digest that. So what we have done is invoked a minimum assumption of rationality and then common knowledge of rationality. And our definition of rationality is that people are not going to play strictly dominated strategies. So we cannot entertain an action that under no circumstances, no beliefs on about what 2 will do, you are going to follow. It's like a no-brainer. If you're not going to follow a particular strategy under any circumstance, then we think that's like a minimal assumption of rationality. You don't self-destruct. You are into maximizing your own payoffs. So this is iterated deletion of strictly dominated strategies. Now, the world would be very nice if all games were like this, that we end up with like a unique rationalizable set. However, that's not the case. Look at the following game. Okay, L, C, R. This is player 2. Player 1 can go top, middle, bottom. I'm going to make out this. These are all examples from Gibbons, by the way. 0, 4, 4, 0, 5, 3. Okay, 4, 0, 0, 4, 5, 3. 3, 5, 3, 5, 6, 6. Okay. Okay. Now, this is a very interesting game. I'll leave it to you to solve. This is in Gibbons. Can you find a set of dominated strategies? Well, if 2 plays left, what should 1 do? 2 plays L, 1 should play what? M, right? 4 is greater than 0 and 4 is greater than 3. 1 should play M. 2 plays C, what should you do? What should 1 do? If 2 plays C, this is what I'm looking at, right? 1's payoffs. 1 should play T. If 2 plays R, what should 1 do? Right here, B. So, there's nothing that, if player 1 is thinking about choosing between T, M, and B, it just depends on what your beliefs are. What is 2 going to do? There is nothing that I can rule out just based on the assumptions of rationalizability. What about from 2's point of view? 2 is thinking, if one plays L, if one plays T now, right? If one plays T, what should T do? Well, 4 is greater than 0 and 4 is greater than 3. So if one plays T, 2 should play L, right? Well, okay. If one plays M, what should 2 do? Then I'm looking at this row, right? So 4 is better than 3, 4 is better than 0. 2 should play C. If one plays B, what should 2 do? Well, 6 is better than 5, 6 is better than 5. 2 should play R. So from 2's point of view, I cannot rule out anything. So here, the entire original game cannot rule out cannot rule out any strategy for either player. The entire original game is in the rationalizable set. Okay? Okay, so I think that's an example. So we need to figure out when we cannot count on iterated deletion of strictly dominated strategies or equivalently rationalizability to lead to some more insight into how to solve this game, we'll have to come out with other methods, and that will naturally lead us in the next lecture to the notion of a Nash equilibrium. I want to just make one more point before I end. Look at this game, okay? I'm only looking at player one's payoffs. So I'm not looking at player two's. Okay? So look at it from player one's point of view. If 2 plays L, M dominates, right? 1 is greater than 1/3, 1 is greater than 0. If 2 plays R, B dominates, right? From player one's point of view. One is greater than 0, 1 is greater than 1/3. So it doesn't look like I can eliminate any strategy. Yeah? However, we will talk a full lecture on this, maybe 2, or what are called mixed strategies. And this is like your first introduction to that. And a mixed strategy is playing a combination of strategies. Okay? And what I mean by that is the following. How about player 1 plays M with probability 1/2 and B with probability 1/2. And I'm going to follow the notion of expected values. So this is expected utility. we know how to calculate expected utility. If player M is playing, if player 1 is playing M with probability 1/2 and B with probability 1/2, so let's say player 1 is following this strategy and we are allowing those combinations, then if 2 plays L, what is 1's best response? Okay, so what does this combination strategy give us? With probability 1/2, right, is playing M and it gets 1. Now remember 2 is playing L, so gets 1/2 of this plus 1/2 gets 0. So this is equal to 1/2. Right? That's in expectation what 1 will get when 1 is playing this combination strategy. If 2 plays right, what will 1 get? Well, with 1/2 playing M and gets 0, and 1/2 playing B gets 1 equals 1/2. Notice, in either case, right, if 2 plays L, the combination strategy dominates playing top. Sorry, playing top. But what do I mean by that? 1/2 is greater than 1/3. So this is if 2 plays L. Similarly, if 2 plays R, the combination strategy dominates playing top. 1/2 is greater than 1/3. So we can think that by using this combination strategy, a rational 1 will never play top. Because in both cases, remember, this is left and right are the only two events in this universe. Either 2 plays L or 2 plays right. There's no in between. I can also see if 2 plays a combination of L and right, and I'll show you when we talk about mixed strategies in more detail. So which means there is no state of the world, and that's my beliefs. Remember, beliefs are probabilities about the state of the world. There's no beliefs that I can hold about the state of the world, i.e. what player 2 would do, that I as player 1 will ever play top. So I can rule it out. So that is dominated, strictly dominated. 1/2 is greater than 1/3. 1/2 is greater than 1/3 in expectation. Okay? So that's the end of this lecture. This is an important point about strictly dominated strategies. We discussed this concept. We talked about iterated deletion of strictly dominated strategies. And we talked about common knowledge of rationality. We talked about rationality first, which is rational players will not play strictly dominated strategies, and then common knowledge of rationality. And then the last point I talked about, so this is 1, 2, 3, 4, 5 is even if a strategy is not strictly dominated by any other strategy, it can be dominated by a mixed strategy of other strategies, which was the last example we did. Okay, so I'll stop here, and we will continue moving on to Nash equilibrium as we go on.